is about delivering data, but data needs to be trustworthy, verifiable, so the whole system needs to be trustworthy. So this session is about verification, validation, building trusted systems in the context of the ECSEL. Without further ado, I will give the floor. We have two speakers, Peter Folkesson from the RISE Research Institute in Sweden. More than 30 years experience in this field of dependable computing. Is interested in safety and interplay between safety and cybersecurity, including verification and validation techniques such as fault and attack injection. So please, without further ado, Peter.
Thank you very much for the introduction. So I will present the Values project. It's ended last year. It's about verification and validation of automated system safety and security. We had a particular focus here on improving methods and tools for verification and validation of security and safety, particularly with respect to time and effort, cost, and so on. So the project overall. It was funded by the ECSEL joint undertaking under Horizon 2020 work program. We started the project the 1st of May in 2020, and we ended the project last of July last year. We had 41 partners in the consortium across 10 countries. So as you can see from the pie charts here, the industrial partners, they dominate. Almost 2/3 of the partners were industrial partners. And the small and medium-scale enterprises dominate here among the industrial partners. But also a large number of large-scale enterprises were in the project. For example, NXP, we had Siemens, we had Alstom, we had Collins Aerospace, and so on. Among the academic partners, the universities dominate. Here we have KTH, University of Coimbra, we had BUT, and so on. And there were a number of research institutes as well, like AIT, Fraunhofer, VTI, and my own organization, RISE, which led the project. The partners were spread across Europe, all the way from Turkey to Ireland. And the total cost for the project was 25.6 million euro. So we had one main high-level objective here in the project, and it was to design, implement, and evaluate state-of-the-art methods and tools that reduce time and cost needed to verify and validate automated systems, and with respect to safety and security requirements. So, related to this, we had a second objective, to design a multi-dimensional framework for classifying the elements of the VNV processes to enable more effective VNV. And we also wanted to demonstrate, verify, and validate the usefulness of the proposed framework. And this we wanted to do with realistic pilots. So, some of the highlights and main achievements in the project. In the beginning of the project, we started detailing the use cases that were going to be used and going to be used as a base for the realistic pilots that we used for the evaluation. And there were 13 use cases, and they were spread across 6 different industrial domains that were part of the project. We had the railway domain, the industrial robotics domain, automotive, healthcare, aerospace, and agricultural domain represented in the project. And for example, in the automotive domain, we had 3 use cases. We had an intelligent traffic surveillance system. We had a car teleoperation system. And we also had a radar system for ADAS. And based on these use cases, we started to identify and detail different evaluation scenarios for each of the use cases. And based on those evaluation scenarios, we specified requirements on safety and security for each of these. And based on those requirements, we derive test cases to be used in the project. And we mapped these test cases and requirements and evaluation scenarios to the framework, the VMB framework that we created in the project. And to aid in the creation of the framework, we conducted a commonality evaluation of the use cases, as well as associated scenarios, test cases, and requirements. So, a central part of our work in the project was the creation of the VMB framework. It turned out to be an 8-dimensional framework that we used to classify the elements of VMB processes. And these dimensions, they include an evaluation environment. It can be done in the lab. It can be done in a closed environment, like a test track. And it can be done in an open environment, like a real-world environment, where you can collect field data, for example. The second dimension was evaluation type. Evaluation can be done experimentally through testing, and it can also be done analytically through analysis. Third dimension was a type of component under evaluation. We had, here we have software, hardware, or a model of the system that we can evaluate. The fourth dimension is the evaluation tool type. The tool used for the evaluation can be either open source or proprietary tool. The fifth dimension is the evaluation stage, where the evaluation is applied, and we align this roughly to a common V process model of development. All the way from initial stages like risk assessment and conceptual stages through design stages, implementation, and testing phases until it's operational. The sixth dimension was the purpose of the component under evaluation. It can be either a sensing component, a thinking component, or an acting component, or it can be doing something else. The seventh dimension was the type of requirement under evaluation. We had non-functional requirements. Safety, cybersecurity, and privacy were part of this project. And we can have functional requirements, of course. The eighth dimension was the evaluation performance indicator, because we wanted to evaluate the improvements we made to the methods and tools. So here we have divided the criteria into two different classes. The first class is the VMB process criteria that targets the performance of the method or tool. And the second is the SPC, safety, privacy, and cybersecurity criteria, which I would say target the capability of the method or tool to evaluate safety, cybersecurity, and privacy, either separately or jointly. And when we had this framework created, we built up a web repository based on the framework, and this we populated with information on the methods and tools that were part of the project, but also information about the use cases and demonstrators and also workflows related to those. So a lot of information in this web repository, a lot of knowledge and data. And we released the web repository to the general public in the end of 2022. Now, for the VMB methods and concepts that we investigated in the project, we had 43 VMB methods in the project, which we identified and detailed. And we divided the methods into 10 different classes of VMB methods that you can see in the diagram here. And this includes both experimental methods, like testing, simulation, runtime verification, fault and attack injection methods, but also analytical methods, like semi-formal analysis and formal verification methods. And the blue bars represent the number of methods in each class. And based on these, you could call base methods, we identified and detailed 41 improved methods. So 41 of these were improved, and these are shown in red in the diagram. And apart from the improved methods, we also created 7 combined methods. For example, the runtime verification method was combined with the fault injection method here in the project. And all these base methods, improved methods, and combined methods were inserted in the web repository. And together with a lot of details about the methods. Okay, in order to measure the improvement that was made to the VMV process using the improved methods, we identified and detailed 15 safety, security, and privacy evaluation criteria. This can be, for example, for safety, it can be the error coverage. It can be for security and privacy, the impact of attacks, for example. But also 13 VNV process evaluation criteria were included here. So these are more targeted towards the performance of the method or tool. And performance can be, for example, time or number of tests required and so on. And based these criteria, we performed a quantitative evaluation of 22 lead demonstrators in the project. And we documented the use of 71 of these evaluation criteria in these demonstrators. Apart from the quantitative evaluation, we also performed a qualitative evaluation where we received over 10 expert responses per use case on 53 questions. And the questions here can be, for example, perceived usability of the method or tool or ease of use and so on. And we also organized multiple demonstration sessions throughout the project where we showcased the achievements so far in the project regarding these demonstrators. Related also to the VMV tools and demonstrators, we created a verification and validation modeling language called VVML. We adapted the VVML language as a plugin for the Enterprise Architect framework. And we used this VVML plugin in Enterprise Architect continuously during the project when we developed and enhanced the tools. It was used in over 40 VMV tools for developing over 40 VMV tools. We also modeled and improved, it was also used for modeling and improving workflows for all the use cases. So several workflows were made for all the use cases here. Apart from that, VVML was also used in the documentation and analysis of results on tooling for virtual prototyping and virtual validation, which was also studied in this project. On the dissemination side, we organized multiple internal training sessions. As you can see in the table, we had 18 internal training sessions on mostly methods, tools, and also standardization, which was also a part of the project. But we also had 13 open training sessions that were open to the external audience. The number of scientific articles published at the end of the project were 94, and this is still growing. We had 8 workshops that were organized or sponsored by the Values project. We had 1 summer school open for PhD students. We organized 2 press conferences, and in the second press conference, we announced the public release of the web repository. And many of the partners in the project that were involved in standardization. So part of the project monitored activities that were relevant to the standardization initiatives, which were relevant to the project. And we also created standardization landscapes for each of the project targets domain. Okay, if you look at the mid and long-term expected impacts of the project, let's start with the technological impact. we had over 40 VMV tools in the project that were implemented, improved, and also evaluated. So we believe that these tools, they implement state-of-the-art VMV methods today. We also think that they played a pivotal role in minimizing the time and cost associated with VMV of automated systems concerning safety and cybersecurity requirements. Apart from the tools, we also had developed a VVML language. And we believe that the verification validation modeling language, which was created, and the workflows that were created using this language can provide significant support to the VMV community. On the economic side, we had, when the project had ended, 2 patents requested, 19 beta test agreements. We had 39 potential agreements with early customers or stakeholders. But we think that additional efforts is needed, for example, for improving the VMV tools. With the recent advances in AI, for example, there I think we think that much can be done to further improve tools. Some tools were improved using AI already in the product, but I think many more tools can benefit from the use of AI. Another thing to look at would be eco-friendly practices in VMV. For example, reducing power consumption when performing VMV. For example, optimizing the use of physical resources like test tracks and move to more virtual environments. Could be interesting. We also think that the values repository, which had 14,200 visits during the 9 first months of its since its release, it could be transformed into the go-to repository for VMV stakeholders. Both the infrastructure and platform used for the repository would allow for this, I think. And we had 85 training, teaching, and academic education activities in the project. So a lot of educational material has been produced, which we think can contribute to the training of future engineers and practitioners in the domain. So this concludes my presentation, and I would like to thank you for attention. Here are some social media links to the project that was set up for the project, and the link to the Values homepage at value3s.eu, and the public web repository is available at repo.value3s.eu. And if you want to follow up on this in the future, you are free to contact the coordinator of the project. His name is Parus Sangshuli, he's a colleague of mine. He's currently on parental leave, but he will be back on, I think, in a couple of weeks. Thank you.
Thank you so much. So, yeah, okay. Let me then now give the floor to Georg Stettinger from Infineon Technologies. He has been involved in ODD-based testing and validation with special interest in certification and homologation of automated vehicles. So without further ado, Georg, please. And now. No. Oh,
You have to click on it with the...
okay, we'll go back.
Let me do it.
Okay,
Wow.
sorry for that. Please.
Thank you very much for the nice introduction. It's a pleasure for me to present the Architect ECA 2030 project, which we had the final review meeting 2 weeks ago. So we are also finished, and we finished very successful. And therefore I want to show you about some important results, especially cross-domains ones, which are important to be shared with our community here. What is the project about? The project is about, when you take a look on the name, about trustable architectures, and we want to achieve, yes, and we develop acceptable residual risks on all levels within those automated vehicles, and this presentation will give you the details what we understand with trustable architectures, residual risks, the absence of unreasonable risk, and how we can build trustable vehicles in the future. From project short facts, we started 1st of July 2020. We had a duration of 24 months. We have 20 partners. You can see all the partner logos on top here from 8 countries. And also it's very worth to mention we built a kind of project cluster with sister projects dealing with very similar topics, and together we can push the topic of lifetime extension, trustable residual risks more than one project can do on its own. What is the project about? I just used here one of our big pictures, so to say. The project will develop residual risk evaluation concepts, validation framework concepts, and of special importance, monitoring device concepts. And to achieve those 3 highlighted results in the middle, we decided to go once to those results bottom up, and on the other hand also top down. Bottom up means the classical way you do in projects. You have a kind of demonstrators defined, you prove the feasibility of those demonstrators, then you extrapolate the gained results to the big picture in that sense, and end up then in demonstrator, independent residual risk evaluation technologies, validation frameworks, and monitoring device concepts. That's bottom up. From top down, we all know a lot of standards, legislations, certification, homologation requirements are present at the moment. How are they influencing our project results? This was the main question we asked ourselves when we came from the top-down approach, and especially ending up in a, how to say, harmonized validation framework, because nothing is harmonized if it's just suitable for one specific use case. So therefore it was also always on our agenda to consider all the requirement sources, the influencing ones here. This big picture can be translated into 5 entire project objectives. You can see them on the very top. 3 blue ones and 2 green ones. The green ones are the societal ones and the blue ones are the pure technical ones. And here, worth to mention, we want to have robust design optimization along the entire ECS value chain. This means the entire architecture of the vehicle, what is the project name is about, is involved. We need a framework for safety validation. You can also see it here as a central element. And the last technical one is we need to identify and manage residual risks, also across all layers. Beside that, trustworthy end-user acceptance is also playing a big role in the project. And we are doing all of that to reduce emissions, crashes, and congestions of future vehicles. Now coming to the results, and one important note in front, when I'm talking about results, I focused on the results which can be used in other projects as well. So not the results which are very project specific, but the general ones, and to spend more time here. And to introduce the results, I want to highlight a very simple but a very important fact here. We all know CCAM vehicles, and we all know there are different layers connected to each other, but when it comes to generate the system requirements and specifications, it's not so easy anymore. And here on the very top you see again the 4 important requirement sources. We have a target ODD where we want to deploy our CCAM vehicles. We have behavior competences, what we want that the CCAM vehicle is able to do. For example, lane changing, braking, overtaking, whatever. All those are behavior competences. That's a target ODD, and we need for every target ODD specific behavior competences that the car can handle this ODD. That's the starting point. And beside that, we have to fulfill legislations, we have to use standards, we have to think already from the beginning in terms of certification. We cannot do this at the very end and say we develop as before and then we will get it certified. This will not work. And we have to consider type approval authorities in terms of homologation, what they want from us. For example, documentation and all those stuff. And then we have a bunch of requirements and specifications, and hopefully ones which are not contradicting each other. I'm saying this because we have European legislations, we have national ones, and we are not always one-to-one on the same page here. And after having those requirements, we can push them down across all layers, starting from the system, the subsystem, components, up to subcomponents, where we end up, for example, in a power or motor controller. And every layer needs to extract the requirements which are affecting this layer. And on the other hand, it's all about checking if everything is working correct during operation. Imagine we deploy a vehicle in a certain ODD. It is certified for that ODD, and we will let it run. Then the story gets started, because as soon as we are certified as a vehicle for one specific ODD and we get deployed, we have to monitor ourselves. Are we within our ODD boundaries or not? And we have to detect if we leave our ODD we were built for, or if everything is fine, we are inside, or for some reason we pushed outside our ODD. What to do then? And this brings me to the health status flow. So when we are monitoring all our layers, subcomponent, component, subsystem, system, we have to define our health status. Is everything fine? Already acceptable but not 100% fine, or critical? And then we have to react on critical situations. And that's why the project comes from. Develop monitoring solutions for all 4 layers within the vehicle to check the health status there. And that's a very complicated task, because we have to understand how to approach this problem of monitoring. And what we did in the project was, let's take the famous Sense Plan Act cycle as a baseline and transfer this thinking to the monitoring domain. And this can be done when we say, okay, we receive information, we collect all status signals which are available on all those layers, also from the previous ones, if we're interconnected and not at the very top-down level. Then we take this information and analyze, is everything correct? So we classify our health status and communicate it to the next layer. And when we do this monitoring task, we have to think about, in case there is an error, can we correct it on the layer where we are? If yes, fine. For example, if we have a redundant component in place. If we cannot, we have to classify how critical the situation is, because we have to tell this to the next layer. If we cannot solve the problem, we hope that at least the next layer can solve the problem. So the last step, transmit the communication of our defined health status across all layers. Why is this transmit point very important and worth to mention? You can see here a chain sketched which should describe the fault propagation. So we always have to analyze in terms of system layer, is it critical when our chip, our sensor, our component fails? Can we continue to run in our ODD or not? And this we can only do if we understand what is the effect of an identified misbehavior on a specific layer up to the system layer. And that's sketched here with the fault propagation. How can this work? I said at the beginning we are also talking a lot about residual risks, and residual risks are strongly connected to the health status. So when we, for example, identify at the propulsion system a non-acceptable residual risk, for example, one e-motor didn't work anymore, or another fault, so we have to think about what to do. If the motor is broken, he cannot maybe heal himself and work furthermore, so we have to communicate it to the vehicle. And the vehicle has now the task to decide what to do. One solution can be reduce the ODD, reduce the behavior competences, and still continue. This means if one e-motor, for example, dies, and I can only run up to 100 kilometers anymore, but my ODD is the motorway, 100 kilometers maybe not the optimal speed, but it's still fine, so I can continue. I have reduced my behavior competences and can still run in my specified ODD. Maybe I have not the capability anymore to overtake because 100 kilometers is too less to overtake. Then I'm maybe just only able to run on the right lane of the motorway. This is a reduction of the ODD from the motorway. So just having the right lane as the lane to run here without overtaking. So it's always a question when we identify the health status here, what is the effect on the system layer? And can we reduce the ODD and or behavior competences and still continue? Of course, this strategy of residual risk reduction has limitations, because if too much breaks down, we are not able to survive in our target ODD anymore. And here we developed a concept which describes it here graphically, how this can be implemented from decision-making point of view. Let's enter again the situation. We have detected an unacceptable residual risk. We have to think about to reduce the ODD and or behavior competences, so more or less shrink those bubbles down. But we have to consider the important fact we need a mandatory overlap of behavior competences and ODD to survive. This means without being able to run 100 kilometers or 50 kilometers on a motorway, we will not have here an overlap, because the motorway needs that speed. We are a higher risk if we run 30 kilometers on the lane than having a stop on the emergency lane, for example. So we always have to check, are we still able to manage the ODD or not? And when we're not able to manage, then we have a very good source to trigger the minimum risk maneuver. What I said, evade on the emergency lane on the motorway and stop the operation, because the residual risk to continue then is too high. What else we developed within the project is a kind of reference homologation process. Sounds very complicated, but is very simple. We tried to collect all present approaches, the state of the art, in terms of homologation. Especially when we think about the project results we know so far, every project does one puzzle of this very complex topic. And we thought, let's start to collect those puzzles and check how can they fit together and if they fit together. And having this big picture in mind, we were also able to identify white spots, which are currently not covered, where are no technologies ready, where are no approaches ready, and this all were summarized in the reference homologation process. It's a kind of manual, one can say, where you can check the state of the art, where you can check what other projects did in that domain, where you can check the life cycle coverage, the compliance to regulations, the compliance to standards. So all topics which play an important role can be looked up in this reference homologation process. Therefore, we call it reference. It should be a guideline to you when you have the task to homologate a system, a subsystem, a component, a subcomponent, where you can look up for methods, processes, tools needed for safety assurance. And this we did with a lot of cooperation with other projects. So we reached out, for example, to the German VV Methods project, which developed some technology bricks. the set level project, and the Sunrise project we heard so far. So all projects dealing with homologation, we tried to get the results and map it into this reference homologation process. Regarding impact, I decided to talk about two topics here. The first one is the impact to the EU ADS regulation. Within the project, we established a strong link to the EU ADS regulation, the General Vehicle Safety Regulation, because of our monitoring activities. When you take a look at the ADS regulation, you have here the pillar 3, it's called in-service monitoring. And that's exactly where our concept of health status monitoring, of monitoring devices, falls into place. In addition, also several high priority topics listed in the EU ADS regulation were covered within the project. We heard about ODD description, we heard about safety targets, residual risks, acceptance criteria, in-service monitoring and reporting. Reporting also worth to mention via our defined communication channels within this health status flow. We have also a reporting concept established, and this brings us to the data requirements here and to the safety assessment. Last but not least, the impact to the European AI Act. It's maybe from the first point of view a little bit a decoupled topic from the project, but when we take a closer look, it is not. There are many similarities between automated driving system assurance and artificial intelligence assurance. Especially we all know the strong interdependence. Getting in every environment perception algorithm uses some kind of AI. So we have already this link established. Coming from the other side, from artificial intelligence, automated driving is just one specific application. So also here, there is a link, and there are many similarities. So we have the EU ADS regulation for automated driving. We have the AI Act on the other side. We have safety assurance in automated driving. We have trustworthiness assurance in the AI domain. So there are significant similarities, and therefore I would especially highlight the call for cooperation, because the common challenges and priorities are the same at the moment. Of course, we have much more in the AI Act. We have 7 requirements, and safety assurance is just linked to one, but that's the most complicated one in the AI Act. And also here we need a standardized deployment and homologation process. The concept of ODD and behavior competences is ready to be used in both domains. We can already observe that the concept coming from the automotive goes to the transportation systems, ending up in aviation, ending up in maritime, and so on. Especially the strong role of ethics and monitoring, disturbance, fault handling, residual risks is present in both domains. Standardization needs are also in both domains there, just to mention 2 of them, metrics, KPIs, but also behavior competences is a big gap at the moment. We have standards for ODD, but no standards for behavior competences. And the last but not least point discussed already, the last talks I was in the room, strong dependence on high quality data sets and scenarios. I think we all agree there, and therefore let me conclude that. Thanks a lot for listening. You can reach out anytime to me for more information. As I said, I focused on the cross-domain summations to be used in other projects as well. Thanks a lot.
Okay, thank you very much, Peter and Georg. My name is Horst Pflügel. I'm from AWL List, and I would like to moderate now the questions that you might have before the lunch. There is already one from. Can you please state your name?
Hello,
and
my name is
ask your
Marco
question?
Tella from Extreme Technologies. So I have a question for both projects because yeah, we are going into some fully automated system, fully artificial intelligence guided system with all the problems that you have highlighted in the last slide. So how we can trust this process? I asked the question for both projects. How do you think? How do you deal with the fact that a human-centric technology, the old-fashioned technologies of the old car, where the driver was the brain of everything and were hearing all the noises of the car to understand if the car was going wrong, if there was something going wrong, or if the noise of the engine was communicating to the needs of reaching a warehouse, let's say in the next 100 or 200 kilometers, with having this human-centric approach also in a fully automated vehicle. How do you deal with this? Do you have you developed this in this project? How is your idea, your perspective?
Okay, very good question. So how to imitate the knowledge of the intelligent user with your modern methods? Please.
Very interesting question. I want to highlight 2 points here. You referred already to the last slide when we're talking about the AI Act. The general term is trustworthy and, very important, human-centric. That's the origin of all 7 requirements. So the AI Act asks exactly for what you mentioned. And related to the project, I have presented many activities related to monitoring. And with monitoring, it's also the main task we as humans are doing in the vehicle. We want to monitor if everything is fine, and then we feel comfortable and continue. And with those monitoring approaches we have developed, the next task is to decide what to communicate to the user and what not. What has to be logged for technical reasons maybe, but what to communicate to the user that the user feels comfortable. Every user wants to understand, okay, everything is fine. And this is exactly the filter between all monitoring tasks and what to communicate to the user is one of the important topics here.
So I'm not working with AI. So I'm not at all working with AI, so I'm not sure if I should comment anything on this, but for sure it's the use of AI. I see many problems. I see ethical problems. I see problems with ensuring that the data has been that was used to train the AI was had good quality. But I'm no AI expert, so I won't delve into any deeper. We can discuss this afterwards if you want. Okay.
Okay. Thank you for that. Okay, already another question.
Good morning. My name is Siets Kaalsvaart from TNO. Hi. I have a question to Georg Stettinger. So you showed, based on the UN ADS regulation, a number of high priorities and medium priorities. And one of the high priorities is completeness of scenarios. So how do you approach, or have you approached this in the project?
Yes, very good question. Completeness of scenarios from our perspective within the project is connected to ODD coverage. So we try to understand which additional value does it bring if we are successfully performing this scenario. To map it in the ODD, and the mapping, the complicated part of the mapping is where will this scenario end up in the ODD? Because if I don't understand this, I have no way to understand when I test something in additional scenario, do I test the same region in the ODD, so it doesn't give me any additional benefit, or another one. So the completeness of scenario is understood in the project in terms of ODD coverage.
Okay, thank you. And then I have a question to Erik Folkesson as well. So you have presented an impressive list of methods and papers about that. And when I had a look at the website while you were presenting, so I see that there's a lot of knowledge-driven methods to knowledge about your system, knowledge about the intended behavior of the system, etc. So how do you connect that to more, or validate the scenarios that you find with more data-driven input?
I wasn't involved I'm trying to connect this to the methods that I was involved in, and I don't see them as knowledge driven actually. Both of those methods I work with, and I don't have a full insight into the other methods. So I can't really tell which one was knowledge driven and
okay. Your colleague was talking about in-service monitoring. Is that also involved in your project? In-service monitoring, so monitoring the product after it's being launched onto the street.
Not that I can recall. No, most of the methods were targeting testing the left side of the V model, or some on the right side, but after no, I don't think so. No. Okay,
thank you.
But I think maybe just a quick add-on, and then we go to the next one. But what CNECT was maybe referring to, so knowledge-driven. I mean, the question is, do you have a requirement for what you expect actually? So what do you do if you have no requirement? And that is maybe also your question. How does it work then? If you don't have a requirement because it's too many. Maybe Georg, if they're missing, you miss requirements because you do not expect that whatever happens on the road, you have to react.
Very interesting question. Again, here I think we can learn something from the AI Act, because the AI Act tells us we have to specify 7 requirements. That's not something very new, but the new thing is during the entire AI life cycle. This means from the very beginning until the very end, and this includes the operation on the street as well. So from that statement, we are forced to think about how to do this, because it's a requirement. We cannot neglect this. If we do so, we are not trustworthy. So here there are many approaches you can take over from the artificial intelligence domain to be fused with automotive business here.
Okay, thank you. Next question.
Yeah, hi, I'm Maciek from Ericsson. So, well, therefore communication technology related question. So we have now emerging cases where communication is also part of something that's then typically function critical. For example, infrastructure mounted sensors, there could be something upcoming. There might be other examples. Is this something you have explicitly considered in your frameworks? Or if not, do you think there is something already existing, for example, wired in vehicle networks where we can leverage on? Well,
of course, communication is an important part. that we have evaluated in the project. Particularly, I think if you look at the cybersecurity requirements, they're often put on the requirement on the communication channels. So these we have evaluated. And what was the second question about the car?
We have examples from any vehicle networks which
Yes.
we might reuse for the wireless communication.
Yes, and that is a trend, and there I see many. Particularly, it depends on the function, but particularly for safety critical functions, we are not close to that yet, and particularly for cybersecurity reasons, I think it's too easy to disturb the wireless communication compared to the wired.
Georg?
A very quick one. We considered the topic of communication in terms of monitoring. This means we monitored the quality of the received signal in terms of delay, in terms of data strengths and so on, because this has a direct effect on the behavior competences. If the communication is not there anymore and we do not have the broad view, I would say 500 meters away, then we are not able to plan overtaking maneuvers in a correct manner because the horizon is too small with in-vehicle sensors. This was a use case we analyzed, and whenever communication is not there, overtaking was shut down because we can try and then see, okay, it wasn't worth to overtake to avoid this situation.
Okay, thank you for that. Any other questions? Then I put the question, maybe a simple one, I don't know. What is an acceptable risk? I think you talk about acceptable risk or residual risk. So when would you say, okay, it's good enough that you, I don't know, there could be a test that you, I don't know if you have children, that you sit your children into a car and say, that's good enough now, I trust it. So I mean that's a question at the end. What is acceptable?
Very good question. Many different viewpoints on that available. Just to mention some approaches, there is, for example, the community of residual acceptance criteria. There is a threshold where you say, okay, human is driving on that level, and if we are driving at least a little bit better, then accepted, everything is fine. When you come, for example, from the SOTIF domain, you have the unknown unknowns which you want to reduce, and to reduce that, starting from an open world context, which is done today, is very complicated and you will never finish. So you have to first put boundaries around the SOTIF concept with ODD, behavior competences, what we have seen. Then you have a manageable space where you can reduce the unknown unknowns. And again here, the link to the artificial intelligence, I know I said it very often, but I have to do it. Because in the artificial intelligence domain, you have a concept of awareness of dysfunctional cases. This means you have to be aware about situations where your AI system is not working. And this awareness gives you a strong hint when is safe enough. But of course, future topic to be harmonized across domains, AI and also automated driving.
Okay, thank you very much for that. Sounds good. Everybody, shall we finish? Seems everybody is hungry. Then, do you want to close? Okay. Then let us thank again Peter and Georg for the good presentations and for answering the questions. Thank you very much.